In the last video, I'll be talking about AC, alternating current, so three-phase current. And I talk about the dam, like the over dam or any other dam, I don't care, with the water flowing, making a magnet rotate, and the magnetic field that is generated by the rotation of the magnet is going to make an electric field, so charges move, and this generates three-phase alternating current. But this is not limited to the hydroelectric generation of the energy. Any kind, pretty much everything we make generates an alternating current. Like, for instance, when we heat up things and we produce gases that are gonna very excited and are gonna rotate magnets to produce a rotating magnetic field, which is going to induce current, and it's going to be three-phase alternate. And even in that case, pretty much everything we do produces an AC three-phase alternating current, except for solar panels. But I'm gonna get to them way later. So for now, let's focus on the three-phase current. Now, it is so much easier to generate current in this way, in three-phase, than it is to generate current in DC, which has been the argument many years ago between Tesla and Edison, between AC and DC, and ultimately Tesla won, and nowadays we use AC for pretty much everything. But as I said, it's way easier to generate current this way. So now, today I want to talk about transformer, because we have covered the very beginning of how the current is generated, but we're gonna get through this up to the way we receive it at home. And we receive an alternating current, but it's not a three-phase, it's a monophase. So we only receive one of those three phases, but there is a long way from the dam, for instance, to your household, and the current has to be carried through. So I'm gonna talk about transformers. Oh no, yeah, I'm gonna use another page. So transformer, what are transformer? Well, let's suppose that you have a dam, okay, here, just like the one okay. I suppose that you have the dam and is generating the current with the way I showed you before. Now, the city you have to carry it to, like with your pretty little household. Yeah, I hate to draw. I hate to draw those things. Because I feel like, I mean, I'm an engineer. I've been to university, but every time I know how perspective works, but every time I gotta draw something, even, the silliest of things, it's like, yeah, just pretend that those are households, okay? So, it's gonna be a very long way to carry current up to the city. So this is the city. This is the dam, like the over dam. And here we're gonna have yeah, the wires are gonna go through here and here. The one that you see, especially in the countryside when you drive, and so on and so forth. When you drive, and you see the electricity being carried through. Okay, so we cannot carry it through a wire like this. We need to go through a transformer first. because the current which is produced, when we go here, we're gonna only get, well, if you live in the US, you get 120 volt, 60 hertz monophase. If you live in the UK, you get 240 volts, 50 hertz. If you live in Europe, like in Italy, Spain, and so on, you get, well, it depends. It gets, well, if you live in India, you get 230 volt, 50 hertz. If you live in Italy, you get 220 volt, 50 hertz. So anyway, let's just focus on those two, and let's just pick 240 volts and 50 hertz. So you get basically a monophase, monophase. You don't get all the three phases. Now, when you carry current and the current goes through the wire, do you remember that at the very beginning we have been talking about how resistivity was defined? You know, at the very beginning when we were talking about Ohm's law, we said that the second Ohm's law was R is equal to rho times L over S. So the resistance of a certain material is proportional to rho, which is a constant, times the length of the, in this case, the wire, over the surface of the wire. Now, if we were to carry the current the way it's carried, so like I suppose that I get 240 volt, 50 hertz, we would have a lot of current going through here, and we will get a lot of resistance from the copper wire. Now, what clever thing we can do is to increase the voltage and decrease the current, because you know we cannot just increase the voltage without paying the price. So if we increase the voltage, the current goes down. If we increase the current, the voltage goes down, and vice versa. So if we were to increase the voltage and lower the current, what happens? Well, we have defined the current as charges flowing, 1 coulomb flowing in the unit of time. So basically, you can think about the current as charges, so electrons moving, okay? And you can think about the voltage as the push that you're gonna give to each and every charge through the wire. So here is the question. Let's suppose that you have a wire here, okay, a real wire with a finite length and a finite surface, so in a finite area. What do you, if you were going to carry charges, so current, for a very, 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 very long distance, what do you want? Do you want a high current and a low voltage, or do you want a high voltage and a low current? Well, what does it mean? Well, do you want a high current and a low voltage? So a high current will be many charges all going together, but very, very slow. So do you want them all slowly getting through this wire? No, you don't. No, you don't, because otherwise they're gonna go so close to the surface that there is gonna be really a lot of resistance here. So the wire is gonna be, well, first of all, it's gonna heat up, because a lot of current produces a lot of heat. So the wire is gonna heat up and eventually it's gonna melt. and there's also going to be a lot of resistance because all those slow charges are gonna try to get all through the wire to get to the end, and that's no good. However, so it's gonna be really crowded here with a lot of them, too many of them. However, so this will be high current and low voltage. However, if we do the opposite and we say, okay, we're going to have a high voltage and a low current, then what does it mean? Well, it means that a low current means that you're not going to have many charges. So you're just gonna bring, by the way, it's not like you were, I'm just saying this because, you know, it's an oversimplified thing to explain. But so high voltage and low current, it means that you're not gonna have so many crowded, many charges that are slow. You're gonna have only few of them, like one, and then you're gonna have another one, and then you're gonna have another one. So only those flowing through the wire. So you're not gonna have all of them, those many charges all getting crowded, stucking into the wire, the conductor. But you're just gonna have a few of them, like one of them, like one, boom, really fast, boom, really fast, boom, really fast, boom, really fast. You're gonna, you know, you're not gonna have all those many of them like in this situation. You're just gonna have a few of them going there, like boom, 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 boom. And this is really better because, you know, in this way they're gonna stay. You can imagine them and staying in the middle, more or less, of the conductor, and there's gonna be way less heat and way less resistivity. So this is the way we do it. We increase the voltage, so you can think about this as the push, and we decrease the current. And you can think about the current as like less crowded. So you can think about the wires as an highway. Okay, we have a finite highway. You're gonna say, okay, you need to get from here, from I don't know, from here to there. Okay, but I'm not gonna let you all of them go through at the same time, very slowly getting through here. I'm just gonna let one of you go through here at a very fast time. So boom, go, boom, go, boom, go. So in order to do that, so to increase the voltage and decrease the current, what do we need? We need a transformer. Now, after all these like 13 minutes of introduction, we're finally gonna get through what a transformer is. So a transformer is an element that basically does this thing of, well, it can either raise the voltage and decrease the current, or do the opposite. So this is how a transformer looks like. I'm gonna do it for monophase, but for the three-phase it's gonna be the same, just that they're gonna be stuck together. So we're gonna have wires going through here. I'm gonna have like this, and then going back like this, and going back like this. Okay, this way. And then from here, I'm gonna have wires going out like this. like this. And I'm doing it intentionally like this. Yeah, I messed up the drawing, but anyway. Yeah, so you're basically going to have, if you have less, well, this is a wire, and this is a wire. If you have less on the left and more on the right, it means that we're gonna raise the voltage and lower the current. So the voltage here is gonna be higher than the voltage here, and the current, of course, is gonna be less. This one is called a step up transformer. So how does it work? Well, there's current flowing here through this wire, and there is no current flowing here yet. Now, what happens? Well, if you recall, I said that when the current is going to flow through a wire, it's going to create, well, if it's going to flow in this direction, it's going to create a magnetic field across the wire, like so. Okay, because of Lenz's law. So here, we can imagine a magnetic field that is created by the current flowing. Now, this magnetic field that is created is going to let the current flow on this side, even though those two are not directly connected. Those two wires are not directly connected. But this wire here, in which there are electrons, is going to feel the change in the magnetic field made by this other wire. And therefore, current is going to flow in this wire. Now, I know what you're thinking. You're saying, okay, I think I understand. So when the current is going to flow here, we're going to make a magnetic, well, the current is going to generate a magnetic field, and this magnetic field is going to make the current flow. Well, yes, but remember, a change in a magnetic field is going to induce current, not just the magnetic field per se. A change in the magnetic field, a change in the magnetic field is going to induce a current. So this is the reason why it works only with AC, and it doesn't work with DC. Why? Well, I suppose that you have a circuit like, I don't know, like, okay, I'm gonna make a simple one. Oops, I almost screwed up. Okay, this plus, this minus, is a battery, and I have, I don't know, a resistance, and then I have an inductor. Okay, so I have like this, and let's suppose that I put another inductor here in another circuit like this. Oh no, let's say that this is not actually resistance. This is a this is like a lamp, like a light bulb. Okay, let's say that this is a light bulb. Now I'm powering this circuit. This is my resistance. This is my inductor. I'm powering this circuit. So we have a resistance, and the current is going to flow through here. And this is this of course is a battery. So battery. So the current is in DC, is in direct current. The current is going to flow here, go through my resistor, go here, and then go all the way back here and back to the source. We have been doing a lot of these type of circuits. Now, what happens here? We have an inductor here, so we're gonna have a magnetic field. So you're basically saying, okay, we're gonna have a magnetic field. So this magnetic field is basically going to make the current flow in this wire as well. So I technically should be able to see the light bulb glow. Not exactly. Yeah, as soon as I'm gonna connect the battery and the current starts to flow, I am gonna see the light bulb light up, but just for a tiny, 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 tiny fraction. And then it's not gonna light up anymore. Why does this happen? Well, because direct current is flowing in this direction continuously. It never stops. Well, it stops when the battery runs out of power. But anyway, it just going in this direction. Therefore, the magnetic field that is generated at the very beginning, and then it never changes. But remember, it's the change in the magnetic field that produces a current. So if the current still goes through here and the direction never changes because we are in DC, then we're gonna have a magnetic field here, which is generated at the very beginning. As soon as I plug in my battery, my Duracell battery, but then it's not gonna change. So I'm not gonna have current anymore flowing here. I'm just gonna have a current, instant current, as soon as I put the battery, and then that's it. So I will have to insert and remove the battery, insert and remove the battery, insert and remove the battery, insert and remove the battery in order to give to the light bulb the chance of even glowing a little bit. Now, if I have AC though, and I'm gonna draw it so that you're gonna be familiar, this will be the same as this one. But in AC, I will have this one. So this stands for an AC, alternating current source or generator. So in AC, if I have my exact same resistance and then an inductor and then the end of the circuit, and then I'm gonna have the same thing here, and this is my light bulb. Whoops. Come on. Okay. So if I do the same but with an alternating current source, so AC source, then what happens? Well, remember we're going to have either 50 or 60 times per second. The current is going to flow in this direction and in this direction and in this direction and in this direction and this direction. So it's going to change direction 50 or 60 depending on where you live times per second. Therefore, the magnetic field that is going to be generated, while here was like north and south and north and south, here it's going to be north and south, but exchange, it's going to change 50 or 60 times per second. Because when the current flows like this, it's going to be north and south. But when the current flows in the opposite direction, it's going to be south and north. So they're going to be opposite, with south and north. So the magnetic field, as I said, is going to be north, south, and south, north. It's going to change. It's going to change 50 or 60 times per second. Remember, nature hates change. So every time that we're going to have a change in the direction of current, the magnetic field is going to have an opposite. It's going to basically be opposite. So north, south, north, south, north, south. So we're going to have a constant change in the magnetic field. And therefore, we're going to have a constant current flowing in this direction, 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 and in this direction. So the light bulb will finally glow. And I'm finally gonna have my photons going out from the light bulb. So yeah, this is how a step-up transformer works, and this is why it's working only in AC. It cannot work in DC, only in AC. Now, you may be wondering, okay, fair enough. We said that we were starting with the DEM, then we plugged everything into a transformer, a step-up transformer, so that we managed to increase the voltage and lower the current, so less heat and less resistance, so that we can carry the current, so electricity, through our wires for very long distances. But then we're gonna get to the households, so it's actually dangerous to get there with a very, very high voltage and low current like that. So we gotta have a step-down transformer. How is a step-down transformer made? Well, it's the same as this one, but opposite. So a step-down transformer so step-down transformer is like, yeah, I'm gonna do it like this, and like this, like this, and like this, and like this, and then the way back here. And here we're just gonna have like this. Oh yeah, I screwed up the yeah, it's something like this. So this one is gonna be the opposite. This one is gonna be a step down transformer, in which the voltage is gonna go down and the current is gonna go up. So we're basically gonna do the opposite. But it works exactly the same. We're gonna have a magnetic field, and the change in the magnetic field with the north and south and south and north, as I showed before, the change in the magnetic field is going to induce the current here, but it's going to be a step down. So the voltage is going to go down and the current is going to go up. So this is how a step-down transformer works. And this is necessary because the current, well, the voltage has to go down because we no longer have to carry through long wires to get to the city. We are in the city, basically. So we had to lower the voltage for safety reason. So now that we have lowered the voltage, we are just gonna get one of the three phases, and we're basically gonna use that for the single household. So each household only receives one phase of the two. Now, well, it's actually different in the US. This is different. This is okay for Europe and the UK. And yeah, the Commonwealth, except for Canada and so on. But it's different for, well, of course, Canada and the US. Because in the US, you do actually have a bus. You have a bus bar. And in the bus bar, you do have, it's like something like this. And you do have two phases, because this one is 120 and this one is 120, so it will be like having 240 overall, but you don't actually get appliances using the 240 directly. Well, it depends. You do have elements connected to the 120 and so on, but in the different things happen in the households in the US. But I'm not gonna talk about this here, otherwise it's gonna be like 1 hour long video, and I don't want that. So just keep in mind that as this is how a transformer works. Now, as a last thing, I gotta say that there are basically 4 groups of transformer. We have group 0, group 5, group 6, and group 11. In group 0, we have 0 degree as an angular, basically if a transformer is in group 0, voltage and current are in phase. A group 5, we have 150 degree. Group 6, we have 180 degree. And group 11, we have 330 degree. And the connection are, in the group 0, we have star, star, and triangle, triangle, which is also called delta. In the group 5, we have star, delta. Well, triangle are just called delta. So star, delta, and delta, star. In group 6, you have star, star, delta, delta. And in group 11, you have star, delta, delta, star. I can actually show you a picture if you want to, just real quick. This is group 0. This is group 6. This is group 5, and this is group 11. So different connection and different angles. But anyway, I just wanted to tell you just for, you know, completeness. But yeah, that's pretty much it for transformer. Oh, by the way, when you see them, you know, especially when you're driving like in your countryside and you just go just a little bit out from your city and so on, that's the step down transformer. Since they're gonna have you know, voltage and current, and they're gonna receive or generate high voltage. If they're a step down transformer, they're gonna lower the voltage and increase the current. A lot of heat is gonna be generated across the transformer. So they're generally, you see them inside something like a box, and inside this box you are basically gonna have oil. They're basically gonna be cooled down using oil, and then something to dissipate the heat, because there's gonna be a lot of heat inside transformer, so they're submerged into the oil. So yeah, that's just one finer note. That's pretty much it for transformer. I hope this helps as always, and keep watching because we're gonna go on.